this, using this formula, or we can calculate tau. Tau equal to VQ over IT. And T, for example, here is the dimension here. This is T. T is the thickness. Okay, so here this the T is the width of the cut we made. Right now, those are the formulas. They only give us the magnitude. They didn't give us any hint about the directions. And now the direction, how to determine the directions, then we think about one step prior to achieving this one. We think about this one, what kind of the loading situations will cause transverse loading like working downward. So basically I talk about is this scenario will be like this. For example, if we consider a beam, I just make an arbitrary illustrations for that case. What loading conditions will cause transverse loading? V as shown above. For example, we see this one. Okay. So for example, here we have a loading P applied at the middle of the beam. Say here is L and here is L. Okay, so now we can draw the shear and bending moment diagram we see. The reaction here is P over 2. Reaction here is P over 2. So here we can draw the shear diagram is like this. So the magnitude is P over 2 and here is minus P over 2. For the bending, the magnitude here is P L over 4, this magnitude. Okay. So, for example, if we would have the beam under loading in the middle, and then we have a shear bending moment diagram, and then I'm going to explain this will have these situations. For example, if I would take a cross section AN here, and then this is a cross section AN. So this side exposed to here, this end is on the other side. I didn't draw it out. Okay. So from here, can you see? On this side, per our sign convention is if we have the cross section facing right, the sign convention for positive V downward. And for our sign convention here, this is our sign convention, right? So right now here, I expose this cross section basically belonging to this category. So here V is positive 2 over P pointing downward, basically is explain the loading situation on the cross section AN. Are we good? Okay, and now once you nod your head and then you agree with me, you can see the bending at cross-section AN is that big. Let me take, I didn't draw that one, let me take the other end. For example, if I would take this free bar diagram as my drawing here, you can see on this end, at this end, the bending equal to 0. At this end, the bending is not big. Okay, so the bending is, for this situation, the bending is bending like this. So that means since the bending stress on this side is larger from the bending stress at the other side. Agree? Okay, so now we're back to our problem. We right now this is give us the calculation of the magnitude, and here I want to use this concept continuously to justify the direction. So let me label it. So this is the cut we made. Okay, and let me expose this cut into this drawing. So let me highlight. So this is the internal cut we made. Okay. And to put highlight on here. So hopefully you see what I did. So right now, this is the free bar diagram of this portion. Okay, and then from here you can see. Right now, using this as one example, now the bending is bending over. For this portion, the bending is bending like this. So that means on this portion, all the bending stress will be pointing into that direction. Right? Agree with me? You look at here. Right now, on this cross section, the magnitude of the bending is that big. It's positive. So that means here is our neutral axis. Now the bending is bending like this way, right? So on this cross section, all the bending is compressive. So the bending is compressive, and then we're taking over the over surface integral. So the equivalent force due to bending stress is like this, right? So that one basically is in magnitude is bending stress over dA, over this cross-sectional area. That be good?
Can you say
Again,
one more time?
Yes. Again, right now from this diagram, we know that the bending on this cross-section is bending like this.
Okay. And then just
So that means all the bending stress on this small cross-section here is compressive. Right?
Yeah,
So
okay.
surface integral give us is the net force pointing into that direction on that area, right? This end, assuming here we take out the case, here is no bending. So here in this way you can see this force, this free bar diagram must be in balance. So that means that on the red internal cut we expect this there have the direction of the force, we call it H, to balance, right? So this H basically is what we obtain is H divided by this area A is our tau, what we did here. We already able to calculate the magnitudes. We don't have to worry about this kind of drawing. Everything is reflected in this formula. Again, one more time, the goal is to identify the direction. So I draw this one. Okay, now we come to the direction. direction of the shear tau is to align to h, right? Because h divided by a equal to tau. This one we can calculate magnitude by doing this calculation, but also direction of the tau should be aligned to the direction of h, right? Doing so much effort, I just want to show you the direction of h is here. Okay, and now we come to the point.
So it's based off just compressive or tension. So if it's compressive, it's going to be towards us, and as tension
The
is going to be.
compression will be going into that direction.
Therefore, H will be coming out of the board.
Yes, to
And
get
then
in balance.
If it was in tension, the
Tension
top
will be
part.
on the other side. Okay. So now we come to here. So that means on this red plane, let me use the small arrow. So basically, that the average shear stress or shear flow will be in that direction. So that means they're flowing from this end to this end on the red dash area. Okay. Good or not? Good, right? Okay. So now locally on the top here, let me select a small area on the top here. Okay, so on the